In today's video, what I want to take a look at is how to actually free this binary tree, right? We have allocated, inside this new node function that we have created in the beginning, we have allocated some dynamically allocated memory on the heap, but we never call free. And I always said that, well, we should always call free for every malloc call, right? But we never do that. Therefore, right now we have memory leaks. In this video, I'm going to show you 3 methods on how to free the binary tree. The third one being the easiest of them all. Right, so this is our binary tree. First things first, we have to think about, well, how many times do we have to call free? Can we just, call free on this node, on the root node, and everything else goes away because, well, it's part of the struct? Well, we can try that out first. So let's go to the code here, and let's just say free of root, right, at the end. And I'm going to compile this, and I'm going to, well, run it using while grind. So I'm going to say that and /main. And as you notice up here, it says that we have allocated 8 times, but you only freed 2 times. Therefore, we have a memory leak. But why is that? Well, as it turns out, if we just free the node itself, we still have pointers to the left and to the right of this node that still point to, well, valid heap memory that has been dynamically allocated. And C doesn't do anything, any such checks to see, oh, you have members in the struct, I'm going to automatically free them if you free the struct itself. No. It doesn't do that. Therefore, we have to manually check to see if we have a left node or a right node to deallocate that as well. So how many free calls do we have to have here? Basically, as many free calls as nodes. But in which order? Well, the basic idea is to simply take the last level of nodes, deallocate them, and after deallocating them, we know that we can deallocate this next part, right? We don't have a problem deallocating 1 and 2 after we have deallocated these guys, and then later on we can deallocate the root. And of course, this should also work if we have, for example, another node here for, let's say, 7, right? Because that would mean that first we'll deallocate this part. But hold on a second, with breadth first search, we kind of had the same idea where we were lastly iterating the last level of the binary tree and firstly iterating the root node and its descendants from there on. So can we just use that breadth first search algorithm to deallocate everything here? In fact, we can do that. Now, in fact, you don't actually have to add anything. You have to just remove the part where we remove any elements from the queue, right? So instead of going from this array to this array, we're actually going to have our array be 0, 1, 2, and simply add things to it. So here, for example, after this step, we're going to take a look at 1 and simply add its descendants. So I'm going to say 0, 1, 2, 3, 4, right? And then I'm going to take a look at 2 and add its descendants. I'm going to say 0, 1, 2, 3, 4, 5, and 6, right? And then all I'm going to do is take a look at these descendants. They don't have anything. And after iterating the whole queue and adding all the nodes to the queue in this manner, we're going to end up with an interesting situation where if we take a look at the rightmost node, for example 6, you will notice that it's always going to be after its parent node. What's the parent of 6? Well, the parent of 6 is 2, and 2 is right here, right? What's the parent of 5? In fact, is also 2, is also to the left of it. What's the parent of 4? Well, that will be 1. What's the parent of 3? That would be also 1. And what's the parent of 2? That's 0. And what's the parent of 1? That's also 0. Therefore, basically, the whole tree has been flattened into this queue, and to the right, you have all the nodes that don't have any descendants, and to their left, you always have their parents, right? So, what you can do is safely iterate from right to left this queue and deallocate each node one by one. So I can iterate from the end, I can just deallocate 6 because I don't have any descendants, I can deallocate 5, I can deallocate 4, 3, and then of course I can also deallocate 2 because we've deallocated every single descendant, right? And I can deallocate 1 because of the same reason, and then I can deallocate 0 as well. And this works for any type of binary tree. So how do we actually implement this? Well, we're going to start with the name of the function, its signature. Let's say free binary tree, and I'm going to say queue, using a queue. It's going to free everything using a queue. I have here a root, and inside of it I'm going to use the same, basically the same structure that we had with the breadth first search, except we're going to remove that removal of elements. So here is that function, and I'm just going to say that and copy that, and I'm going to paste it here. Well, what do we actually need to change? Well, this initialization and adding the root to the queue as the beginning, that's perfectly fine. We're not going to change that. This condition is going to have to change. We'll see later on how we change that. And this removal of elements is going to have to change completely, right? So I'm going to remove this whole thing. I'm going to remove this processing part, this printf. I don't care about anything here. And what I want to do here, well, I need to change this line, because right now if we if we try to use this code, we're always going to access the same element, right? We're going to access process queue of 0, which is the root, and we're just going to keep on adding the root's descendants to the queue. So we need to change that. How? We're going to have an index here. Let's call it I, and I'm going to say int I. It's going to start at 0, and that's where the condition change comes in. So I'm going to change this condition to be while I is less than the process queue number, right? So of course, after taking the ith element, so in the beginning would be the first element, then I want to increment this to go over 1 and iterate over the next nodes on the list, on the queue, literally. So I'm going to say I++. Now, after having all the queue set up, we can actually just iterate over that queue and deallocate all the nodes. That's very simple. The only thing that we have to keep into consideration is the order of deallocation. We have to go and iterate from right to left. Okay, so we're going to have here a 4. I'm going to use the same I here. I think that's perfectly fine. We're just going to have process queue num -1. That's the last index of the queue. I higher or equal than 0, and of course I minus minus. And then we can just say free of process queue of I. And doing that will actually deallocate the whole tree. So now if we try to call this, so say free binary tree using a queue, I'm going to call it with root. And if we try to compile this, and if we try to use whilegrind to check if we have any more memory leaks, you can notice that in use at is 0 bytes, and we have 8 allocations with 8 frees. Now there are a couple of limitations with this. Of course, first things first, there's a memory limitation. You actually have to have a place to store all the nodes of a binary tree, which might or might not be possible. Secondly, you have to iterate over both the binary tree and the queue twice, right? Therefore, this is not that optimal, but it's kind of easy to think about, right? Right, now let's figure out the second method for freeing the binary tree. And that actually has an interesting observation that you have to make. Whenever you are iterating over, for example, the root node, we would always be pushing 1 and 2 to the list, right? So our list would look like this. So we have here 0, right? That's perfectly fine. But then we would be iterating over 0, and we would add both 1 and 2, right, to the list. Therefore, do we actually still need that 0? Can we just deallocate it right after pushing the elements in this array? In fact, we can. We can simply deallocate this 0 right after pushing the elements, because they are not, the pointers to its descendants are not lost. We have them in the queue already. Therefore, one thing that you can do is, instead of freeing them here, you can change the free call to be inside the while loop. So you can free current right after adding all of its descendants to the queue. And now, if we try to compile and check this with whilegrind, you will notice that we get the same result. That's amazing. We removed one of the problems, and that was iterating over the queue again. We don't have to do that anymore. But there is one small problem. We still need this process queue, and this process queue actually still has to have enough space to fit all the nodes. So even though we are freeing these nodes, right, even though we are doing free of current, that node will still be in the queue, and this process queue num will still go basically will still go as high as the number of nodes in the binary tree, right? If we have 30 nodes, this process queue num will be 30, and we'll have 30 pointers inside our queue. Can we do something about that? Well, as it turns out, we can. Remember the depth first search algorithm? We used a stack, and we didn't have to remove anything simply because we were decrementing the last element that we took out, and we were replacing it with its descendants, if any, right? And we can actually do the same here. We can simply use this iteration with a stack instead of a queue, and that would actually result in not having to use an array that can hold all the nodes or pointers to all the nodes to our tree. So I'm going to create here another function, void, let's say free binary tree using stack and tree node root. I'm going to just paste everything here because it's actually going to be very, very similar. So we still have the same initialization, nothing different here. We still have the same condition. It's just that instead of processing, all we do is add the elements to the stack and simply free current, as we did up at the other optimization. And you might ask yourself, well, aren't we still allocating here a stack of 100 elements, and isn't this the maximum number of nodes that our tree can have? Well, not really. The stack, right now, the free algorithm has a limit of 100, but not 100 nodes. It just has a limit of about a binary tree that is 50 in depth, right? It depends exactly on how many nodes you have how many descendants you have per node, but for example, if you only have one descendant per node, you have a binary tree that looks basically like a linked list, then the limit would be 100, right? But usually in the real world, a binary tree would branch off in many places and rarely even get to 100 levels, right? Therefore, this algorithm also doesn't use that much memory to deallocate the whole binary tree. So we can try and launch this. We can just say here stack, and if I compile this and again run it with valgrind, you will notice that again all the nodes have been freed. To better understand this memory efficiency, I think it's better to exemplify using our binary tree and going step by step through the algorithm. So here we start with the stack with just the node 0, right? Our n is going to be equal to 1, right? Let's put here 1. And what do we do in our while process here? Well, first things first, we decrement the n, right? So we're going to say n minus minus. In our case, n would become exactly 0. All right, and then we add to the stack the new, well, the descendants of the node that we taken out, right? Therefore, we're going to overwrite first things first, process stack of n, which is 0, then increment this n, right? It's going to become 1, and then we're going to add to the stack process stack of 1, and again increment it. Therefore, we're going to end up with 1, or actually 2, and 1 on the stack. And n will become, and from then on, we just take the last element. So here, for example, we take 1. Again, we decrement n will become 1 here after we take this out and we free it. And we're going to add its descendants. So we're going to add 4 and then 3 onto the stack, right? We're going to do 4 and 3. And then n, of course, will become 3. And I'm going to stop keeping track of n here, but we're going to keep track of the stack itself, right? So next up, we take 3 from the stack. Nothing really happens. So we just free that and we don't add anything new. We take out 4 from the stack. And again, nothing really happens. We just end up with a stack that only has the 2. And then we take 2 out of the stack and we push 6 and 5 onto it. Right, we have here 6 and 5. Right, 5 doesn't have any descendants. We take 5 out of the stack, we only end up with 6, and then of course the stack remains empty after we free 6. So, as you might notice here, this stack doesn't become too large. What is the maximum size of this stack? Well, the maximum size of this stack is actually just 3, where we have 2 for free, and that's about it. We never really add more than 3 elements to it. So for this binary tree, in fact, we can just have a stack of size 3 and everything would work perfectly fine, right? Whereas with the queue implementation, you will have something like this. You have here a 0 and you have also an I pointer or an I index here, right? That points to the first element. And first things first, we add the new descendants to the queue. So we add here 0, 1, 2, and we change I to point to 1 now. But we only deallocate 0, but we don't actually overwrite this part of the queue. So there's going to still be a value, that would be still that address to where 0 used to be allocated. Now it no longer is allocated, but that space will still be taken up by this algorithm. And if we continue on, so if we take a look at 1, the next step would be what? Well, we would basically end up with 0 here that is deallocated, with 1 here that is deallocated, with 2 still here, and we would have the descendants of 1, which are 3 and 4. So 3 and 4 would be added here, and I would now point to this 2, and so on and so forth. Basically, this grows as high or as large as the binary tree. Therefore, you're going to have a queue that can store all the nodes of the binary tree, whereas in this situation, you only have to have, for example, for this specific binary tree, 3 spaces in the stack allocated. Now there's one last method that I want to talk about, and that is the most obvious one, but not the most efficient one. And that is using recursion. So using recursion and using the process of, well, basically first deallocating your descendants and then freeing the node itself, you can deallocate the whole tree in about a few lines of code. So what I'm talking about, well, is basically iterating over the root node and calling the same function with your left and right descendants. And then on this call, on the call for this, for example, this descendant, we're just going to call the same function for this guy and this guy. And only after we have iterated over all descendants, or we don't have any, we actually free this node, right? So in this case, this would be freed, and then this would be freed, and then this would be freed, and everything would just basically free itself using recursion. How do we implement that? Well, it's actually very simple. We can just say here, free binary tree, let's say recursive tree node. I'm going to call it node this time because it's not always the root. And all we have to do is say if node arrow left is not null, then simply call the same function with node arrow left. And the same thing for the right side of things. So I'm just going to say left, right. All right. And after we have freed our descendants, right? So think about when we were iterating over the root node. After we have freed both this and this, then we are safe to just free the whole node itself. So we can just say here free of node, right? And this function is going to be called for all the nodes. If we try to launch this, let's change this to free recursive. I'm going to compile it, and then let's say here var grind. You'll notice that the same good result we got, that we are not leaking anything. This is the easiest way to implement free on a binary tree, but this recursive approach is not really the most efficient, simply because you are creating stacks for every call, and in our case we are going to call this function 7 times basically, and at least we're going to have to allocate enough space for this pointer on the stack, right, that we have here on the signature, and more work for the computer to jump around to return the result and not return it. Therefore, I don't really recommend this. Definitely the iterative approach is much more efficient. But the nice thing about it is, if you cannot figure out how to implement the iterative approach for whatever tree you're working with, not even binary trees, this recursive approach is very simple to also think about, right? All I had to do was think about that, before freeing the node itself, we have to free first the descendants. And using this simple process, we were able to simply create a recursive function that runs just fine. And that's about it regarding freeing the binary tree. Again, I hope you got something out of this video. If you do have any questions, leave them down comments below or on our Discord server. Again, the source code can be found on the description down below. Take care. Bye.